What is up? I'm here. You're there. We're going to do some 7-5 stuff. You guys ready for this? Are you ready? Are you ready, though? Sure you are. Okay. So we're talking about our exponential functions now, right? So we've seen linear functions, right? Now we're going to see exponential functions. These will not be a straight line on a graph. We have two different kinds of functions. Think of them just like we think of slope, right? We have slope that goes uphill. We have slope that goes downhill. We read it like a book. The same thing here. We have a growth function and a decay function. All right? Exponential growth functions, okay, on a graph will look like that. Yeah, they also go that way too, okay? That's what growth functions look like. What do decay functions look like, right? Again, growth ones are growing, they're going uphill. Decay ones doing the opposite. They're starting up high and they're going downhill. Okay? Read them like a book. That will help you figure out if it's growing or decaying, declining, decreasing. Okay? All right, so there's what they look like. Exponential function asymptote. This is a really weird word. So asymptotes are only found on exponential graphs. And they're really confusing because the graph appears to get to this number, but in reality, it never really quite does, okay? And in class, we're going to show some exercises, probably with Desmos, where we zoom in and we show that, hey, like it looks like this red line eventually is going to get down here to the x-axis, right? Which is the number 0, all right, at y. But it never really will. It'll get really close to it, but it never will, right? Neither will this blue line I drew here. It's going to get super close to 0, but it will never get there. Those we call asymptotes, right? They are lines that approach a number, but never, ever, ever get to it, okay? Fun words there. Okay. Here is our exponential form, right? This is like standard form for us, crew. Y equals AB to the power of x. You'll hear me say this all the time, okay? Well, what does everything mean? Kind of like how we had like y equals mx plus b, and we know that x and y are just the two variables, input, output. M is the slope, b is the y-intercept, okay? Well, I wonder if b is the y-intercept here. Interesting, we'll have to see, okay? A, this is the initial value, okay? This is the starting quantity, right? This is how much we start with. And then maybe we're growing, maybe we're decaying. Okay, B is the growth rate. Okay? We can be growing by a certain percentage. Hey, it's growing by 15%, 20%. Or it could be doing one of the weird growth rates. It's doubling, it's tripling, quadrupling. Okay? Again, x and y always stay exactly where they are. They're just x and y, right? Input, output. In this case, the x is actually the exponent of this, okay? Again, here are some examples, okay? 2 times 3 to the power of x is how we would say that, right? So this has an initial value of 2, right? Its growth rate is 3, meaning it's tripling over time, okay? Y equals 4 to the power of x. That's quadrupling over time. What's its initial value? Well, it doesn't have an a value here. It does. There's those dumb invisible ones again. Okay, y equals 1/2 x. Again, initial value of 1. This one has a number smaller than 1 for its growth rate. 1/2 is how it's growing. Okay? It's not really growing at all if it's 1/2. It's decaying. But we'll see that here in a second, guys. That'll all make sense here. All right, so a couple things we got to do. It says graph this. Well, it already graphed it for me very nicely. Again, you're going to have to look carefully on Desmos because if we just kind of zoom out, it's just going to look like a line that's going vertically because these functions grow or decay so fast they almost look like straight vertical lines, okay? So find the y-intercept, state the domain range, and equation of the asymptote. Okay, so y-intercept, super easy, guys. Where does it cross the y-axis? Right down here, that would be at the ordered pair 0, 1. Or you could just say the y-intercept is 1. Domain and range. Domain. Okay, so again, scan left to right. Are there any x values that this function will not get to? No. Right? However you want to write it. All real numbers. Negative infinity is less than x is less than positive infinity. Right? Brackets. Okay, don't care. All mean the same thing. Range, a little bit different. How low does it go? How high does it go? And this is where we have to see the asymptote. Okay? I promise you, this graph will not get to 0. Right? It's starting up here, look, and it's going this way. It looks like, heck, it already looks like it's there, but it's not, I'm telling you. Okay? So, the range, how low does it go? Well, it gets close to 0, but it never really gets there. So, I would like y values that are greater than 0. I don't know why I'm putting in curly brackets, but I just am. Okay? You could say 0 less than y less than positive infinity, right? Or you could say 0 to infinity. These are all great ways. Okay? The equation of the asymptote. Well, guys, this is the asymptote right here. Okay? It is a horizontal line that goes through 0 on the y-axis. Right? How do we name that? With the equation y equals 0 is how we name that. Okay. Good to go. Guys, hey, we're going to keep doing this with a whole bunch of other examples. So, graph this one. Do we get a graph at any point in time? Which we do not. Okay. Graph this. All right. So, we could graph it. Okay. And... so this will be at the ordered pair 1, 5. This is at the ordered pair 0, 1. There you go. All right. Is that all we had to do? Sure is. If they asked us the same questions, guys, y-intercept 1. Okay, domain and range. Domain, all real numbers. Range is identical. Y values greater than 0. This also has an asymptote at y equals 0, as most of them do, right? Most of them will have this horizontal asymptote, okay? All right. Same thing we got to do here. Y-intercept, what is it? It's right there. It's at 1, okay? So find the y-intercept. We did that once. State the domain, range, and equation. Same thing here. Domain, left to right. Left, right, left, right. All real numbers. That hasn't changed. Okay, range, up and down. Once again, it looks like it's getting down here to 0, but I promise you it's not. If you're not sure, go check it out on Desmos. Okay? So it doesn't get any lower than 0, nor does it include it. And it goes all the way up to Buzz Lightyear's favorite number, to infinity and beyond. Okay? So range, y values greater than 0. Parenthesis, 0, comma, infinity, parenthesis. Okay? Once again, the equation of the asymptote hasn't changed. Still, y equals 0. Hopefully you're writing all this down. Okay? Don't need to do anything there because it didn't write it down. Guys, you'll notice, right, when we see these graphs here, these are exponential decay functions. There you go. Look at that. Super good looking one there. Okay? Again, this is the ordered pair 0, 1. And then like this down here is going to be 1, 1/8. No, this is not by chance. This always works in this scenario, guys. When we don't have a number in front of here, like an a value, always going to be at 1. Okay? Whatever this number is, right? Think about it. If I take x to the first power, right? Well, what's 1/8 to the first power? It's just 1/8, okay? Hence, when x is 1, y is 1/8. This is math. This is why this works, okay? Anyway, there's our graph of that. Again, this is an exponential decay function. It's decreasing, going downhill, right? Read it like a book, folks. Okay, so if we have a graph, I'm betting you're pretty good at recognizing increase or decrease. But what if we just give you the function itself? Well, all we have to do is look no further than the b value, okay? B value, 1/8, decreasing. B value, 1/4, decreasing. B value, 4, increasing. Okay? All right. Here we go. Here's our function. It models the depreciation of the value of a new car that originally cost that much money, $25,000. Okay? V is the value of the car, T is time in years from when you first buy it. Graph the function. Okay? So here, let me give myself a little bit of room. Here's what this function looks like, guys. V equals this 25,000.82 to the power of t. Okay, so if we're going to graph this function, this is the value, right? This is time. Okay? What's happening to the value of the car over time? Well, we probably all know. I go buy a car today, in a year, 2 years, 4 years from now, is it worth as much as I bought it for? No, it's not, right? So this is going to be one of those decreasing functions. Now, where should it start? What's your initial value? 25,000, right? So again, we're just going to say this is 25,000 right here, okay? So we're going to start here, and then it's decreasing. This is a number smaller than 1, right? It's 0.82. What's 1 minus 0.82? 0.18, and what is that as a percent? 18%. So that means the value of this car is going down 18% every year. Well, think about it, right? So if we go down 18% every year, right? Here goes. You know, the value of that car is going to go down, but is it ever going to be worth nothing? No. And that's why, right, when we talk about horizontal asymptotes, right, it's going to approach zero. At some point, that car is not going to be worth much money. But is it ever going to be worth nothing? No. No, it's not, okay? So there's my graph of it. Hopefully that makes a little bit of sense. What values of V and T are meaningful? Well, the values of V that are meaningful would be from 0 to 25,000, right? So V values would go from 0 is less than V is less than or equal to 25,000, okay? Because that's just the value of the car, right? It will never be worth anything more than 25,000, nor will it be worth anything less than 0. Okay? We could probably just leave that at 0. That'd be okay too, or greater than. Okay, what values of time make sense, guys? Can we start here at negative time? No, we sure can. Okay? So 0 for time, and then like what value makes sense at the end, right? How far can we keep going here? Well, I mean, we can't go to infinity, can we? No, probably not. I mean, I would say probably 50. I'm sure the book has some super smart answer for this one, right? But we just want to know, hey, it's got to be some time greater than 0. How long are we really going to keep a car for? I mean, unless it's like the sweet vibe car that Mr. Knoll has. I don't know that we're going to keep it forever. Okay, here's another function, right? It almost looks identical. The initial value is a little bit less, but that 0.82 looks very suspicious. Again, this one models depreciation. Here, our initial value of this car was $22,000, okay? Graph the function. So, again, super easy to graph this one. Guys, you'll notice most of our graphs really are just dealing with quadrants 1 and a little bit of 2. Okay? Again, here is the value. Here is the time. Guys, what's my initial value? 22,000. How am I decreasing? Well, I'm decreasing at 18%. You don't have to be super you know what I mean, accurate, you just got to have the general shape, right? Which is, hey, it's decreasing really fast and then it slows down, okay? So good to go there. All right, here we go. Now we get to use this function for something. So here's my function, right? 22,000, and then this 0.82 to the power of t, okay? And it says, yes, we know this function represents the value of the car at any particular time in years. And we need to figure out what is the value of the car after 1 year, okay? So if we want to do that, again, is year a v value or a t value? Obviously, it's a t value. So we're going to take that number, or that time frame, 1, and we're going to replace it in here. And then we're going to grab our handy-dandy calculating machine. And we're going to figure out what this is. Okay? So guys, I'm literally just going to take that 22,000 number and multiply it by 0.82 to the first power. Now, you don't even really need to write that in, but there you go. There's your answer. Okay? So the value after 1 year, unfortunately, this is the way the world works, gang. The value of your car is only $18,000. Okay? Have you ever heard the expression, someone's upside down on a loan? Well, this is what this means. After 1 year, you might not have paid off, right? You might borrow $22,000 for that brand new car, right? And 8 months from now, you get into some kind of an accident, right? Maybe the car gets totaled. Well, hey, the value of that thing's only worth this much, but you haven't paid off. It's not below that. So yeah, these are all pig. You don't have to worry about any of this for a long time. Okay? All right. I digress. What else do we have? Okay, so we've done a couple things. Let's think about all the different things we've done. We've identified exponential functions, right? We've given some domain, range, equations of asymptotes, right? We've graphed them. We had some scenarios involving exponential functions, and we're just plugging in numbers. It's not that bad. And then the last thing we're going to do is figure out, hey, does this table or this graph exhibit or have exponential behavior? Unfortunately, we can't just ask it, hey, are you a well-behaved exponential function? We can't do that. But here's what we can do. When things are linear, right, we know they make a straight line on a graph. Okay? So, like, if something's linear, bam, my x values increase at the same rate. My y values will also increase at the same rate. Like, hey, maybe my x values are going up 4, and my y values are going up 2 each time, right? That would be good. Well, let's look at my x values. How am I getting from one x value to the next? Oh, I'm adding 10. Okay? So that makes me happy because we're adding the same number. Great. Well, if we're exponential, guys, we're not looking for addition or subtraction. Okay? Because think about it, we are exponentially growing. We're growing by a factor, right? Or a percent. So we got to do a little bit of multiplying or dividing, okay? So here's what I like to do. I like to take the second term divided by the first term. So 25 divided by 10 is 2.5. Take 62.5, divide that by 25. 62.5 divided by 25. Ha 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 ha. 2.5. I can't stop here. I got to check this last one. A 156.25 divided by 62.5. It's that same number, 2.5. Okay? So we found this number, right? Divide to find. Okay? What did we do up here? We subtracted to find here. Okay? So does this one have exponential behavior? Absolutely. It's growing by what factor? By a factor of 2.5. Okay? Beautiful. Same thing here. What do we think about this one? Again, easy to see. My x's, are they going up or down by the same number? Yeah, they're going up by 10. and up by 10 and up by 10. Okay, well, what about the y's? Well, 50 divided by 100 is 1/2. 25 divided by 50, also 1/2. 12.5 divided by 25, also 1/2. Okay? So does this one have exponential behavior? Yes, it does. Okay? And look, as we would notice, if we tried to subtract here, right? Hey, this minus this, okay, that's going to be what? Negative 50, and then here's negative 25, negative 12.5, right? So we would automatically think, hey, something doesn't look right here. Okay? So that tells me it's not linear. Okay? And eventually that's when we move on to say, okay, well, if it's not linear, what is it? Well, in this case, now we know it could be exponential. If we give it another chapter, it could be quadratic. Tough sometimes to figure out the difference between quadratic and exponential, but good news, we ain't got to worry about that right now, okay? Only thing we got to worry about is finishing up here with 7-5. So guys, we should have bookwork, quizzes, and all the other fun things I have planned for you. So good luck with that. You were great today. Good job.